Mars has resiliently weathered asteroid impacts, global dust storms, and 4 billion years of bombardment by cosmic rays. But it has never faced an entity quite like Atlas. Three-eyed. This interstellar visitor carries ice and chemical compounds, forged under a foreign sun, and its approach to Mars is the very first test of humanity's understanding of cosmic threats from beyond our solar neighborhood. On October 3rd, the encounter could unfold like a captivating dance, a familiar one. Or it could trigger a cascade of catastrophes, transforming Mars from a future home into our greatest cautionary tale. From the scenario of an impact creating a 30-kilometer-wide crater to the risk of contaminating the entire planet with alien chemicals, the range of possible outcomes is immense. Tonight, we will explore why the worst-case scenario may not be a direct impact, but something far more subtle and potentially much more permanent in its consequences. Stay with us until the end of the video to understand why the most concerning outcome might not be a collision, but something far more insidious. Part 1. October 3rd. The Moment of Truth. Mark. October 3rd, 2025 on your calendar. Because this event will never happen again. On what seems to be an ordinary Friday, something extraordinary will unfold. In the space between worlds, a celestial dance may rewrite the rules of planetary safety as we know them. Three-eyed Atlas, our mysterious visitor from beyond the stars, will glide past Mars at a distance of about 30 million kilometers from us here on Earth. This distance might sound safe, about 75 times the distance from the Earth to the Moon. But in the world of interstellar visitors, this is what astronomers call a worryingly close encounter. The European Space Agency has been tracking this encounter with a tense precision, usually reserved for defusing a bomb. But their calculations paint a picture of somewhat wild celestial mechanics. Atlas does not behave like the gentle comets we are familiar with in our solar neighborhood. Ever since it was first discovered, this object seemed to carry within it a cosmic rebellion, and 3/10 could be the moment it completely lost its interstellar composure. Consider the evidence that has accumulated like storm clouds on a summer horizon. Atlas had created a cloud of carbon dioxide gas of staggering proportions. It was a swirling shroud of gas stretching for millions of kilometers in every direction. Most comets reserve their most impressive displays for when they are closer to the sun. Yet, Atlas appeared to disregard that specific rule. In the cosmic playbook, its outbursts of brightness were equally concerning. Multiple observatories had reported flares that appeared suddenly and then vanished just as unexpectedly. These were not the gentle, predictable changes we would expect from a block of ice slowly melting under the sun's gaze. These were the erratic convulsions of something fundamentally unstable, something that might be trying to hold itself together by sheer cosmic will. NASA's Spitzer Space Telescope had been working overtime to classify these anomalies, and the data it gathered painted a picture that would make any planetary defense expert nervous. The shape of the gas plume was unusual. The gas emissions followed patterns that didn't align with our models. Even its orbit carried subtle signs of disturbance, suggesting this was more than just a dirty snowball from the far reaches of another star system. But here is where things become truly concerning. As Atlas approaches its closest point to Mars, we are entering a period that astronomers historically call an observational gap. Solar conjunction. The time when Mars, the Sun, and Earth align in a way that makes observation nearly impossible, is fast approaching. For the next few weeks, our ability to monitor this cosmic object will be severely limited. Just think about that for a moment. At the very moment Atlas reaches its most critical phase, when its proximity to Mars could trigger the most dramatic events, we are essentially flying blind. This is like trying to watch a high-stakes poker game through a keyhole while blindfolded. The timing could not be more suspicious, as if it were orchestrated by some malevolent cosmic intelligence. The universe seems to have a twisted sense of humor, making us guess at the fate of our planetary neighbor. The scientific community is walking a fine line between professional skepticism and a barely contained sense of panic. Rapid changes in a comet's activity are often precursors to fragmentation events, when a comet becomes active. 7. Often, when its surrounding coma brightens unexpectedly, when its jets follow chaotic patterns. Experienced astronomers will begin to prepare for the possibility that the object may soon disintegrate. Now, imagine that fragmentation event not happening in the safe depths of interstellar space, but right within Mars's sphere of influence. Picture ancient chunks of ice and rock, kilometers in size, suddenly liberated from their parent body, each one sent hurtling on its own trajectory, through the gravitational labyrinth of the inner solar system, with some potentially spiraling toward the sun, increasing the population of potentially hazardous objects, while others could collide with planets that have spent billions of years in peace. Models from the European Space Agency suggest that, even without a direct impact, the gravitational disturbance from a major fragmentation event could push some debris into Mars-crossing orbits for many years, or even for many decades to come. We could be witnessing not just a close encounter, but the seeding of a cosmic minefield that will haunt our efforts to explore Mars for generations. What makes this scenario particularly worrying is our lack of understanding about the true nature of Atlas. Its enormous coma has obscured our view of the actual nucleus within. We do not know whether we are dealing with a single, massive object or a loosely bound collection of fragments, held together by gravity, or something even stranger. The luminous veil that makes Atlas so visually spectacular may be hiding a cosmic time bomb, whose detonation could scatter debris across multiple planetary orbits. NASA's Science Mission Directorate has been suspiciously silent about specific contingency plans, although internal sources suggest that many Mars orbiters are being repositioned to gather any possible data throughout the encounter. The Mars Reconnaissance Orbiter, MARO, the MAVEN spacecraft, and the European Space Agency's Trace Gas Orbiter, TGO, are humanity's eyes and ears at Mars. If something dramatic were to happen on October 3rd, these robotic sentinels would be our only witnesses to the events that could reshape human understanding of interstellar visitors. But even these sophisticated instruments operate under significant limitations. Their cameras and spectrometers were designed to study Mars, not to track cosmic debris hurtling at high speeds. Their communication systems were built for routine data transfers, not for broadcasting emergency bulletins about planetary cataclysms. If Atlas decides to put on a truly spectacular show, our assets at Mars might find themselves completely unprepared for that cosmic fireworks display. The promise of this investigation extends far beyond mere scientific curiosity. We will follow the evidence wherever it leads, even if it takes us into territory that makes our safe planetary assumptions seem dangerously naive. We will examine impact scenarios that keep planetary defense experts awake at night. We will explore atmospheric effects that could turn Mars into a toxic wasteland. We will consider the possibility that contamination could complicate humanity's plans for Martian colonization for centuries to come. Most importantly, we will ask the questions that official agencies seem reluctant to discuss publicly. What if Atlas does more than just fly by? What if October 3rd marks the beginning of something far more perilous than a mere fascinating encounter? The answers might surprise you, or even terrify you. But one thing is certain. After October 3rd, nothing in our relationship with interstellar visitors will ever be the same. The impact scenario we are about to explore is just the tip of a cosmic iceberg, with its depths extending far deeper into the realm of planetary catastrophe than most people dare to imagine. Part 2. The impact scenario. The mathematics of cosmic destruction are surprisingly elegant. When astronomers calculated the probability of Atlas actually hitting Mars on March 10th, the initial numbers seemed quite reassuring, with a distance of 0.19 to 0.2 astronomical units. The laws of geometry suggested that a direct impact was somewhere between astronomically improbable and physically impossible. But mathematics, much like democracy, works best when everyone follows the rules. And Atlas, as we've established, seems to be a cosmic anarchist. Consider what would happen if one of those mysterious fragmentation events we discussed earlier occurred at the worst possible moment. Imagine, Atlas had persevered through 30,000 years of interstellar travel, only to break apart like a cheap firework, just as it entered Mars's gravitational sphere of influence. The parent body might continue on its predicted trajectory, skimming harmlessly past the red planet, but the fragments, they would play by their own rules. Each piece would carry its own momentum, altered by the chaotic forces of the breakup event. Some might accelerate toward the sun, others could be flung outward, beginning their own solitary journeys toward the stars. But a few pieces, perhaps only a handful out of hundreds of fragments, might find their trajectories bent just enough by Mars's gravity to turn a near miss into a direct hit. Consider the scale of destruction to understand what we are truly dealing with. A fragment between 100 and 500 meters in size, roughly the size of a city block, would slam into Mars at a velocity that makes a rifle bullet look like it's in slow motion. The kinetic energy released would be equivalent to thousands of nuclear weapons detonating at once. The resulting impact crater would be several kilometers wide, but that would only be the beginning of Mars's troubles. Mars's atmosphere is thin and composed mostly of carbon dioxide, offering almost no protection against incoming objects, unlike Earth's thick atmospheric blanket, which can burn up smaller objects and slow down larger ones. Mars is nearly naked against the cosmic assault. The impact energy that would be partially absorbed by Earth's atmosphere, would instead be delivered directly to the Martian surface with its full, undiminished force. The immediate aftermath would transform Mars into a world that the robotic explorers who have studied it for decades would scarcely recognize. The ejecta from the impact, composed of pulverized rock and ancient permafrost, would be hurled high into the thin atmosphere, creating a global dust storm that would make the seasonal storms we have observed seem like mere breezes. The opacity of the Martian sky would soar, far beyond anything ever recorded in its history. Within just a few hours, the entire planet would be enveloped in a suffocating shroud of suspended particles. The solar panels on the rovers and landers would become useless, deprived of the sunlight they need to operate. Temperatures would plummet as the dust spread, blocking out the incoming sunlight, triggering a nuclear winter effect that could last for months or even years. But the electromagnetic chaos might pose an even greater threat to our technological assets than the dust itself. The impact would generate a high-intensity electromagnetic pulse, as charged particles from the blast interact with Mars's tenuous magnetic field. These electrical pulses could induce currents, damaging electronic systems, potentially disabling the spacecraft that survived the initial blast. The Mars Reconnaissance Orbiter, MAVEN, the Trace Gas Orbiter, and the Mars Express, our electronic ambassadors orbiting the red planet, would suddenly find themselves operating in an environment more hostile than anything their designers had ever anticipated. The robotic explorers might lose their ability to navigate. Communication systems could be overwhelmed by radio interference from the ionized debris cloud. Solar arrays could be damaged by the high velocity of particles accelerated by the impact. On the surface, the consequences would be even more severe. The Perseverance and Curiosity rovers, along with the InSight lander, were designed to withstand the typical dust storms on Mars. But a planet-enveloping dust storm caused by a cosmic impact is a challenge on a completely different level. Communication with Earth would become highly irregular as atmospheric conditions cause disturbances. Radio transmissions. The radiation environment around Mars would spike dramatically as the impact excavates subsurface materials and lofts them high into the thin atmosphere. The thin atmosphere which provides Mars, with only minimal radiation shielding, would become saturated with charged particles, creating hazardous conditions for any future human explorers. Even robotic systems would face an increased risk of radiation-induced errors. Now, let us escalate the scenario to a truly apocalyptic level. What if instead of a single fragment, multiple pieces of Alas found their way to Mars? What if the fragmentation event created not just one city block-sized object, but 10 such objects? The cumulative impact would push Mars past a mere bad day and straight to the doorstep of planetary catastrophe. Multiple impacts would generate overlapping clouds of ejecta, turning the entire planet into a chaotic storm of debris. The combined electromagnetic effects would create a planet-wide radio blackout lasting for months. The dust opacity would reach levels that completely block solar radiation, triggering a global ice age that could alter Mars's climate for centuries. But this is where the scenario becomes truly concerning for those of us still safe on Earth. The gravitational chaos created by the multiple impacts could alter the orbits of Mars's two small moons, Phobos and Deimos. These massive rocks are already in a precarious state. Phobos is slowly spiraling inward and is destined to crash into Mars. And though that is about 50 million years away, a major disturbance could significantly accelerate this process. If ejecta from the impacts were to strike Phobos with enough force, or if the gravitational perturbations from the Alas fragments destabilized its orbit, we could witness the destruction of a moon in real time. The debris from such an event would form a ring system around Mars, but not the elegant, stable rings like those of Saturn. Instead, we would see a chaotic cloud of rocky fragments that would present a navigational hazard for centuries to come. The psychological impact on Earth would be profound. Mars represents humanity's next frontier, a backup plan and a second chance for us to become a spacefaring civilization. Witnessing it transform into a desolate, irradiated wasteland, surrounded by the debris of its own destroyed moon, would be like watching our future crumble before our very eyes. However, even this catastrophic vision pales in comparison to the possibility that we have been thinking too small. What if the real danger is not mechanical destruction, but something far more subtle and potentially more permanent? What if the 3/10 encounter brought not just rock and ice, but something that could poison the potential for human life on Mars, in ways we are only just beginning to comprehend? The atmospheric shockwave scenario we are about to explore does not even require a single piece of debris to actually strike the planet. Part 3. The atmospheric shockwave. Forget everything you think you know about cosmic collisions. The most insidious threats from Atlas might never actually reach the Martian surface. Mars's defense system against attacks from space, to put it mildly, is pathetic. Unlike Earth, which cocoons itself in a protective magnetic field that deflects most charged particles, Mars stands almost naked before the solar wind. Its global magnetic field died billions of years ago, leaving only scattered magnetic anomalies. These cosmic scars serve as tombstones for the planet's once protective shield. This magnetic nakedness makes Mars extremely vulnerable to effects that Earth's magnetosphere would simply shrug off. As Atlas grazes past Mars, trailing its enormous carbon dioxide tail and potentially shedding debris, it would not create a conventional Hollywood-style shockwave. There would be no compressed wall of air rushing across the Martian landscape at supersonic speeds. Instead, we are looking at something far more subtle and potentially more devastating, a cascade of electromagnetic and particulate effects that could fundamentally alter the chemistry and electrical environment of the Martian atmosphere for months, even for many years. Imagine Atlas as it approaches Mars, with its core ejecting gas and particles in chaotic outbursts, which we observed throughout 2025, each outburst creating clouds of ionized material, essentially plasma that interacts with the solar wind in complex ways. When this ionized mixture encounters the faint remnants of Mars's magnetic field, it doesn't simply bounce off, it penetrates, it swirls, and it creates electromagnetic vortices that can persist long after Atlas has continued on its trajectory. The immediate effect would be a significant enhancement of Mars's already rare auroral displays. instead of the faint, localized lights that Mars occasionally produces. We could witness planet-encompassing light shows as charged particles from Comet Atlas flood into the upper atmosphere. These auroras would not be the romantic displays, gentle ones we often see in Earth's northern regions. They would be intense, chaotic storms of light, disrupting radio communications and potentially damaging sensitive electronics. But these visible effects are just the tip of the electronic iceberg. This event would cause chaos in Mars's ionosphere, the layer of charged gas in the upper atmosphere that our orbiting spacecraft rely on for communication. As Atlas's charged particles interact with this region, they would create periods of radio blackout that could last for weeks. Think about the implications for our robotic explorers. The rovers on Mars are accustomed to reliable communication windows with Earth. These are carefully scheduled communication sessions, where they upload their discoveries and download new instructions. An ionospheric disturbance could sever these digital lifelines, leaving these billion-dollar robots stranded on an alien world, unable to report their status or receive guidance from their controllers. The electromagnetic chaos wouldn't stop at the ionosphere. Mars's thin atmosphere makes it particularly vulnerable to electrostatic effects that are almost negligible on a world with a dense atmospheric blanket. As the debris from Atlas interacts with the Martian environment, it could create similar conditions, like massive dust storms, which already rage on this planet, but enhanced with electrical energy. Imagine dust storms in which every particle carries a significant electrical charge, creating electrical storms that would dwarf anything we have ever witnessed on Earth. These would not be the relatively benign static discharges that we typically observe during thunderstorms on Earth. They would be high-energy plasma arcs, capable of damaging surface equipment and creating radio frequency disturbances, making communication with Earth nearly impossible. The scenario becomes truly alarming when we consider Mars's tendency to form global dust storms that envelop the entire planet, which can be triggered by seemingly minor events, a slight temperature difference in one place, a pressure change in another. The electromagnetic disturbance from Atlas's approach could provide precisely the kind of trigger needed to push the Martian atmospheric system past a tipping point, leading to one of these global dust storms. But this is where the atmospheric physics becomes truly unsettling. What would happen if the passage of Atlas did not just trigger a conventional dust storm, but created an entirely new phenomenon in the history of planetary meteorology? What if the combination of charged particles from the comets, dust cloud, and the existing Martian atmosphere created a self-sustaining feedback loop? Envision this nightmare scenario. Atlas's charged debris creates initial electromagnetic disturbances in Mars's upper atmosphere. These disturbances then generate static electricity in the lower atmosphere, charging the dust particles and making them more easily lifted into the air. The amount of atmospheric dust increases, altering the planet's energy balance, creating temperature and pressure differentials, which in turn sustains the storm. Meanwhile, the charged dust particles continue to interact with the remnants of Mars's magnetic field, perpetuating the electromagnetic disturbance. The result would be a planet trapped in a state of near perpetual electromagnetic and meteorological turmoil. A grim feedback loop could last for many years after. Atlas has continued its journey toward the edge of the solar system. Mars will become a world of never-ending dust storms, where radio communication is a matter of chance, and where the radiation environment is so chaotic that even our most durable robotic explorers could suffer electronic failures. NASA's spacecraft designers had anticipated many challenges for operations on Mars, but they had never had to deal with an electromagnetic vortex on a planetary scale. The high-gain antenna of the reconnaissance orbiter on Mars might have to constantly battle interference from charged dust clouds. The particle detectors on the Maven spacecraft, which were designed to study the gentle interaction of the solar wind with the upper atmosphere of Mars, could be overwhelmed by the chaotic particle environment created by Atlas's passage. The public relations issue would be an immediate and profound nightmare, as images from Mars become sparse and communication windows disappear. Speculation would run rampant. Social media would explode with theories about what is truly happening to our robotic emissaries on the Red Planet. Official denials and technical explanations would be overshadowed by more sensational stories of cosmic disaster and government cover-ups. But perhaps the most troubling aspect of this scenario is how it would be misunderstood by the public. Mars would not actually be on fire in any conventional sense, as carbon dioxide gas does not support combustion like oxygen does. But the global auroras, the constant lightning from charged dust storms, and the strange electromagnetic phenomena would create a visual effect that could easily be mistaken for planet-wide destruction. The scientific community would find itself in an awkward position, trying to explain that Mars was not, in fact, on fire, while also having to admit that the planet had indeed become temporarily uninhabitable for human exploration. The distinction between chemical combustion and electromagnetic chaos would be lost on a public already primed by decades of disaster movies, always expecting the worst interpretations of cosmic events. However, even as we contemplate these electromagnetic nightmares, we must acknowledge that the atmospheric chaos on Mars might not be the worst-case scenario. What if Atlas brought to Mars something far more persistent than electromagnetic storms, and far more dangerous than charged dust clouds? What if the real threat was not physical or chemical, but biological? Contamination from another star could fundamentally alter not only the immediate future of Mars, but also humanity's long-term relationship with the Red Planet. The contamination scenario that we are about to explore operates on a timescale that makes the electromagnetic storms seem like fleeting summer breezes. Part 4. Contamination from another star. The theory of panspermia, the hypothesis that life travels between worlds on cosmic debris, has fascinated scientists for many decades. But when that cosmic debris originates entirely from another star system, the implications become so profound they could keep astrobiologists awake at night. Atlas presents us with a disturbing possibility that it seems no one in the scientific community is willing to discuss openly. This interstellar object has spent at least 35 years traveling through interstellar space, its core acting as a cosmic deep freeze, preserving whatever molecular cargo it might have collected during its formation in a distant star system. The vast carbon dioxide coma that Atlas has generated, in turn, provides a perfect chemical environment for complex organic molecules to survive and even evolve during its interstellar transit. Carbon dioxide is not just a simple waste product. It is also an excellent solvent for organic chemistry, capable of stabilizing complex molecular structures across the range of temperatures and pressures that Atlas experienced throughout its journey. NASA's James Webb Space Telescope has conducted a spectral analysis of Comet Atlas. Although the results are still preliminary, the infrared signatures detected so far have confirmed the presence of carbon dioxide gas, water vapor, and what mission scientists have diplomatically described as complex organic compounds. But the true nature of these organic components remains hidden behind layers of technical analysis and peer review. Could take months to complete. Meanwhile, the spheric mission had been monitoring subtle changes in Atlas's outgassing, suggesting something more dynamic than the mere sublimation of frozen gases. The observed patterns did not align with the behavior of typical comets when heated by sunlight. Instead, they hinted at chemical processes that might be occurring right within its coma, possibly catalyzed by cosmic radiation or intrinsic chemical reactions that had been proceeding slowly but steadily throughout the object's interstellar journey. Current planetary protection protocols are specifically designed to prevent cross-contamination between worlds, but they are tailored for spacecraft traveling between planets within our own solar system. No one had ever seriously considered what would happen when a potential alien ecosystem might land on Mars without undergoing any sterilization procedures. The encounter on October 3rd could introduce organic molecules to Mars, molecules of a kind that have never existed on any planet. in our solar system. These compounds, having evolved under the chemical conditions of an alien environment, could interact with the Martian soil and atmosphere in ways our models cannot predict. They might catalyze reactions that alter the planet's chemical equilibrium. They could introduce molecular templates capable of interfering with future searches for native Martian life. Consider the nightmare scenario, the one that has planetary protection experts reaching for their emergency contact lists. Exotic organic molecules from Atlas integrate into the Martian regolith and begin to self-organize into structures that mimic biological processes. They wouldn't necessarily be alive in any sense we would recognize, but they could be active enough to alter the local chemistry, consume resources, and spread through environmental mechanisms. Such pseudo-biological activity could render Mars inhospitable to human life, long before we ever develop the technology to establish permanent colonies there. Imagine trying to set up life support systems on a planet where the very soil has been contaminated by self-replicating chemicals that we do not understand and cannot control the risk assessment for. Human missions would have to be completely rewritten. Even more concerning is the possibility of false positives in experiments. For future life detection, the exploration of Mars has always been driven by the tantalizing prospect that we might discover evidence of past or present life on the red planet. Sophisticated instruments are currently being developed for future Mars sample return missions, designed to detect subtle chemical signatures that could indicate biological processes. But what happens when those instruments encounter organic molecules that are not native to Mars? How can we distinguish between native Martian biochemistry and contamination from an interstellar visitor? These scientific implications could set back our understanding of Mars by decades, as researchers struggle to separate the local signal from the cosmic noise. The contamination scenario becomes even more complex when we consider the potential for atmospheric dispersal. If Atlas's approach triggers the kind of global dust storm we discussed earlier, any organic particles deposited on the Martian surface could be swept up into the atmosphere and spread across the entire planet in a matter of weeks. What might initially be a localized contamination event could quickly become a planet-wide phenomenon, affecting every future landing site. NASA's current Mars exploration timeline includes ambitious plans for manned missions in the 2030s. These missions depend on the assumption that Mars is a relatively predictable environment, where life support systems can operate reliably and where in-situ resource utilization can provide the water, oxygen, and even the fuel necessary for a sustained human presence. Organic contamination from Atlas could completely undermine these assumptions. Water extraction systems could become clogged by foreign organic compounds. Atmospheric processors could become overwhelmed by chemical reactions they were not designed to handle. Even the psychological impact on the crew could be devastating. Imagine being the first people to set foot on Mars, only to discover that the planet has been fundamentally changed by contamination from an interstellar visitor. The time to fully understand these impacts could last for decades, unlike impact craters or electromagnetic storms which show their consequences relatively quickly. Chemical and biological contamination, however, unfolds over a much longer time frame. We might not fully understand what Atlas has done to Mars until the 2060s or later. The scientific community is facing a particularly difficult dilemma when publicly discussing these possibilities. Acknowledging the risk of contamination could be seen as fear-mongering, undermining public support for Mars exploration programs, which have taken decades to develop and billions of dollars to implement. But failing to acknowledge these risks could leave future missions unprepared for environmental conditions that differ significantly from current models. International space law offers little guidance for scenarios involving contamination from interstellar objects. The Outer Space Treaty and subsequent agreements were drafted with the goal of preventing human-caused contamination, not the transport of chemicals from the cosmos. If Atlas were to contaminate Mars, there would be no clear legal framework to assign responsibility or coordinate an international response. The contamination scenario also raises profound questions about planetary ethics. Do we have the right to continue exploring Mars if that exploration could be compromised by contamination we cannot control? Should future missions be postponed until we better understand what Atlas might have brought to the Red Planet? These are not just technical questions. They are ethical questions that could reshape humanity's approach to space exploration for generations to come. However, even as we confront these biological nightmares, we must remember that Atlas operates in a realm where physics can become chaotic. The gravitational dance between planets, moons, and cosmic debris follows rules, could yield far more dramatic results than mere contamination. What if the October 3rd encounter didn't just alter the chemical composition of Mars, but fundamentally disrupted the gravitational relationships that have kept the Martian system stable for billions of years? The scenario of orbital chaos that we are about to explore operates on a scale that makes biological contamination look almost trivial by comparison. Part 5. Orbital Chaos. Phobos and Deimos, the two tiny moons of Mars, have been described by astronomers as captured asteroids, irregular chunks of rock that Mars snared with its gravity at some point in the distant past. But these cosmic prisoners can hardly be considered model inmates. Phobos, the larger and inner of the two moons, is already on a slow death sentence, spiraling inward, toward an inevitable collision with Mars in about 50 million years. Under normal circumstances, this timescale would give human civilization ample time to settle Mars and figure out how to deal with the moon collision situation. But the approach of Atlas on October 3rd introduces variables that could dramatically accelerate this cosmic doomsday clock. The actual gravitational pull from the Atlas encounter presents us with an interesting paradox. At a distance of 30 million kilometers, the comet's direct gravitational influence on Phobos and Deimos would be negligible. It's the equivalent of the gravitational pull of a large building on Earth trying to affect the orbit of the Moon. The simple math doesn't support scenarios where Atlas reaches out with invisible hands to grab Mars's moons and hurl them into new orbits. But chaos theory teaches us that small influences can have large consequences when systems are already close to a tipping point. And as it turns out, Phobos exists in a state of gravitational imbalance, making it extremely sensitive to even the slightest perturbations. This moon orbits Mars at an altitude of only about 6,000 kilometers, so close that it completes 3 orbits for every Martian day. This proximity places Phobos well within Mars's Roche limit, the distance at which tidal forces from the planet would overcome the moon's own gravitational pull. The only thing keeping Phobos from disintegrating immediately is the internal strength of its rocky structure, and even that is slowly giving way to the relentless tidal stresses. Recent observations show that Phobos has developed stress fractures, parallel grooves that could be the early stages of tidal disintegration. The moon is being pulled apart bit by Mars's gravity with each orbit. It is a cosmic debt, by 1,000 cuts playing out over millions of years. Now, let's introduce Atlas into this delicate gravitational dance. The comet might not exert enough direct gravitational force to have an effect, but it carries something potentially more dangerous: debris. As Atlas glides through Mars's gravitational neighborhood, it could shed material that crosses the orbital plane of the Martian moons. Even the smallest particles moving at interstellar velocities carry enormous kinetic energy. A grain of sand from Comet Atlas's trail hitting Phobos at 20 kilometers per second would impact with the force of a small explosive device. Multiply this by thousands or even millions of particles, and you begin to understand how a cosmic encounter that seems gentle can become a devastating bombardment. The cumulative effect of such impacts could be enough to push Phobos's already stressed structure past its breaking point. Instead of slowly disintegrating over millions of years, the moon could shatter catastrophically during or just after Atlas's passage. What was once a slow-motion cosmic demolition project could become a sudden burst of debris, But let's take this scenario to its most plausible extreme. What if Atlas not only accelerates the destruction of Phobos, but also creates something entirely new in planetary science history? What if the collision generated enough debris to form Mars's very first ring system? The physics of planetary rings are more complex than most people realize. Saturn's elegant ring system represents a delicate balance between collisions and electromagnetic effects, which has taken millions of years to achieve stability. A ring system created by the violent fragmentation of Phobos would be nothing like the orderly bands of ice and rock of Saturn. Instead, Mars would find itself surrounded by a chaotic cloud of debris on wild, elliptical orbits. Some fragments will be large enough to pose a serious hazard to spacecraft operations. Other fragments will be small enough to create a persistent micrometeoroid environment that could erode solar panels and optical equipment over time. The navigational challenges for future Mars missions would become a nightmare. Instead of planning orbits around two predictable little moons, mission planners would have to contend with thousands of fragments moving in unpredictable orbits. The risk of collision would increase exponentially, potentially making Martian orbit too hazardous for routine spacecraft operations. But orbital mechanics has a cruel sense of humor when it comes to cleanup operations. Unlike ground-based pollution, which can sometimes be remediated through human intervention, orbital debris follows immutable laws of physics. Each collision between fragments creates even more debris, each piece following its own orbital path. This process feeds on itself, creating a chain reaction that could last for centuries. This phenomenon is known among space operators as the Kessler syndrome, a runaway chain reaction of orbital collisions that renders entire regions of space unusable for practical activities. We have worried about this phenomenon, affecting Earth's orbital environment for decades. But Mars, with its weaker gravitational field and thinner atmosphere, might be even more vulnerable to such a cascading destruction. The psychological impact on humanity's dream of colonizing Mars would be profound. For decades, we have envisioned Mars as our backup planet, our second chance to build a sustainable civilization beyond Earth. To watch that future literally crumble before our eyes would be like witnessing the destruction of humanity's greatest aspiration to reach beyond our home planet. The recovery time could be measured in geological millennia. Unlike atmospheric storms or even chemical pollution, orbital debris operates on the slow but inexorable laws of celestial mechanics. Debris from the destruction of Phobos could continue to endanger operations on Mars for thousands or even millions of years. However, even this scenario pales in comparison to the possibility that we are thinking too locally about Atlas's destructive potential. What if the October 3rd encounter at Mars is not the end point, but merely the first domino? In a chain of gravitational interactions that could ultimately threaten Earth itself, the physics of orbital perturbations operate on timescales that make human planning horizons seem laughably short. A small gravitational nudge today might not manifest as a significant threat until decades, or even centuries, in the future. As we prepare to explore the chain reaction scenario, we must confront the unsettling possibility that Atlas's brief encounter with Mars could initiate a sequence of events that will ultimately bring cosmic catastrophe to our very doorstep. Part 6. The Chain Reaction to Earth. In cosmic terms, distance offers only an illusion of safety. NASA's current projections indicate that Atlas will make its closest approach to Earth around December 2025, at a distance of approximately 1.8 astronomical units, or about 270 million kilometers. By any reasonable measure, this is a safe distance, one that should preclude any direct threat to our planet. But the solar system operates as a web of interconnected gravitational influences, where the butterfly effect can manifest on a planetary scale over a long period of time. What happens at Mars in October will not just stay at Mars. It will propagate outward through the complex gravitational relationships that bind our solar system together, creating a ripple effect that could take decades or even centuries to fully manifest. Consider the mathematics of orbital perturbation theory. Every gravitational interaction, every encounter, no matter how small, slightly alters the trajectory of every object involved. The flyby of Atlas near Mars will inevitably change the orbits of both bodies by a very small amount, changes measured in meters per second that seem utterly insignificant in the context of planetary velocities measured in kilometers per second. But those tiny changes would accumulate over time through a process known as gravitational resonance, just as a small push applied at the right moment can set a massive pendulum swinging. Small orbital changes can accumulate over many passages through the solar system's resonant zones, from what begins as an imperceptible nudge can gradually become orbital changes measured in thousands of kilometers. The immediate concern relates to the debris. If Atlas were to experience the kind of fragmentation seen in the Mars impact scenario we have explored, the fragments would not simply disappear after colliding with the red planet. Each piece would continue on its own altered trajectory through the inner solar system, creating what astronomers poetically call a long-term hazard environment. Some of these fragments might find themselves in an orbit resonant with that of Earth, creating periodic encounters that could last for many decades. Other bodies might be perturbed into highly elliptical orbits, bringing them into the inner solar system at unpredictable intervals. The result would be a subtle yet measurable increase in the background flux of potentially hazardous objects threatening Earth. NASA's planetary defense infrastructure has made significant strides in recent years. The Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, are designed to provide years of advance warning, or even decades for most objects large enough to cause localized damage. They are calibrated to detect objects following relatively predictable orbits within our solar system, the fragments of Atlas, on chaotic trajectories influenced by their interstellar velocity and multiple gravitational interactions, might not fit the standard detection profiles. Their approach angles could be unusual, their velocities unexpected, and their composition different enough from typical asteroids to confuse automated classification systems. The time frame for these threats could span generations, unlike the immediate drama of a single event. Collisions or atmospheric disruptions. Many types of gravitational interactions operate on what physicists call secular timescales, meaning slow but relentless cumulative changes over periods measured in decades or centuries. We may not fully understand the consequences, from Atlas's October 3rd encounter with Mars until the 2040s or beyond. This delay in consequences creates a particularly insidious form of cosmic risk. Politicians and space agency administrators making decisions about planetary defense funding today may no longer be in office to face the consequences of their choices. When the Atlas-derived fragments begin to threaten Earth in the 2050s or later, the Yarkovsky effect further compounds these concerns in a way that makes long-term prediction nearly impossible. This subtle phenomenon occurs when small bodies absorb sunlight during their day and re-radiate that heat during their night, creating a small but continuous thrust that can significantly alter an orbit over long periods. For the fragments of Atlas, which may be composed of exotic interstellar materials with thermal properties unlike anything in our solar system, the Yarkovsky effect could produce orbital evolutions that defy all current models. Imagine this nightmare scenario unfolding over the next 55 years. The fragments of Atlas, initially deemed harmless by computer simulations based on conventional asteroid behavior, gradually drift into Earth-threatening orbits through unforeseen Yarkovsky drift patterns. By the time ground-based telescopes detect the threat, there may not be enough time to mount effective deflection missions. Precedent for such gravitational chain reaction disasters exists in our solar system's history. The late heavy bombardment, which occurred around 4 billion years ago, may have been triggered by gravitational resonances, destabilizing the orbits of the outer planets, sending a cascade of comets and asteroids into the inner solar system. The craters on our moon are permanent reminders that gravitational chaos can transform peaceful regions of the cosmos into a shooting gallery. But Atlas introduces variables that previous bombardments never had: interstellar velocity, exotic composition, and fragmentation patterns that may not follow the rules established by billions of years of our solar system's evolution. We could be facing a new kind of gravitational cascade chain, something for which our solar system's history has no precedent, and our models have no reliable basis for prediction. The impact of the meteor shower alone could be spectacular, in the most terrifying sense of the word. Earth regularly collides with debris from known comets, creating predictable annual meteor showers, which delight amateur astronomers and generally pose no threat beyond the occasional satellite impact. But a meteor shower from the fragments of Atlas would be something else entirely. This would not be the gentle light show of the Perseids or Geminids, where tiny particles burn up harmlessly in Earth's atmosphere. The fragments of Atlas, moving at interstellar velocities and potentially composed of materials that do not behave like common meteoroids, could produce airburst events, rivaling the Tunguska explosion of 1908. The Tunguska event flattened 2,000 square kilometers of Siberian forest, the result of an object estimated to be only tens of meters in diameter. Now imagine multiple Tunguska-level events occurring as Earth passes through the debris streams from the fragmentation of Atlas. The cumulative effect could devastate entire continents over decades. The vulnerability of modern civilization to such events has increased exponentially since 1908. Power grids. Our communication networks and transportation systems create cascading points of failure that did not exist in the Tunguska era. A single air burst event over a major metropolitan area could cause economic crises and prolong societal disruptions. For many years, the insurance industry has begun to grapple with the consequences of increased cosmic risk. Lloyd's of London and other major insurers have been quietly developing models for events like space weather that could affect global commerce, but their current risk assessments assume that potentially hazardous objects will be detected years in advance, allowing for an orderly evacuation and the reinforcement of infrastructure. The fragments of Atlas follow chaotic and unpredictable orbits, and could arrive with much shorter warning times, potentially leaving both emergency management systems and insurance markets completely unprepared. The economic impact could dwarf the immediate physical damage, creating a corridor of heightened cosmic risk that lasts for decades. Perhaps most concerning is the possibility that we are already locked into this future, regardless of what actually happens on the 3rd of October. The gravitational perturbations that will ultimately determine Atlas's long-term effect on the dynamics of the inner solar system may have already been set in motion by the comet's initial approach. Orbital mechanics operates according to deterministic chaos, systems in which small initial differences can produce dramatically different outcomes, but where those outcomes are nonetheless inevitable once the initial conditions are set. We may be living through the early stages of a preordained gravitational cascade. Ever since Atlas first entered our solar system several months ago, the monitoring systems that could provide early warning of developing threats face their own vulnerabilities in an era of increasing cosmic chaos. Ground-based telescopes can be hampered by atmospheric conditions, while space-based observatories can be damaged by the very debris fields they are designed to detect. Communication systems that relay threat assessment data to planetary defense networks could be disrupted by the electromagnetic chaos we explored in the Martian atmospheric scenario. But even if our detection systems worked perfectly, even if we spotted every fragment of Atlas decades before it threatened Earth, we face the sobering reality that our defense capabilities are still largely theoretical. The DART mission successfully demonstrated that we can alter the trajectory of an asteroid, but only under carefully controlled conditions involving a known target. With a predictable composition and orbital characteristics, the fragments of Atlas, with their strange interstellar origin and chaotic orbits, may not respond to deflection efforts after breaking apart. In the way our models predict, we could find ourselves in a position of knowing exactly when and where a cosmic disaster will strike, but be powerless to prevent it. This is the true horror of the chain reaction scenario. It is not the spectacle of immediate planetary destruction, but rather the slow-motion catastrophe of witnessing our cosmic neighborhood become increasingly hazardous over a timescale that exceeds human economic and political planning horizons. We may be witnessing the beginning of the first cosmic crisis indirectly caused by humanity itself, triggered by our expansion into a solar system that was never as stable as we once thought. However, even as we contemplate these terrestrial nightmares, we must acknowledge that the robotic emissaries currently orbiting Mars face more immediate and existential threats. The spacecraft, our eyes and ears at the red planet, operate on engineering principles that never anticipated encounters with interstellar chaos. What happens when advanced space technology meets cosmic forces that follow no earthly rules? Part 7. Spacecraft in Peril. Space, though romanticized in science fiction, is fundamentally a hostile environment for the delicate electronic systems that extend humanity's presence beyond Earth's protective embrace. Our spacecraft are achievements of precision engineering, complex assemblies of sensors, processors, and communication systems that must function flawlessly in an environment where the slightest malfunction can mean mission failure. Martian orbit presents unique challenges, pushing spacecraft design to its absolute limits. The radiation environment, while not as intense as Jupiter's lethal magnetic fields, still degrades electronic components over time. Micrometeoroid impacts, though infrequent, can disable critical systems with surgical precision. Extreme temperatures fluctuate between the freezing cold of Martian shadow and the harsh heat of unfiltered sunlight, causing thermal stresses that gradually fatigue even the most durable materials. But the engineers who designed our current Martian fleet, including the Mars Reconnaissance Orbiter, MAVEN, the Mars Express, and the Trace Gas Orbiter, never anticipated having to operate in the chaotic environment that the passage of Atlas could create. These spacecraft were built to study Mars under normal conditions, not to survive a cosmic catastrophe. Consider the inherent vulnerabilities in modern spacecraft architecture. The high-voltage electrical systems essential for operating sophisticated instruments across the vast distances of interplanetary space become a liability when exposed to the kind of electromagnetic chaos that Atlas could generate. Static buildup from the bombardment of charged particles can create voltage differentials that arc across circuit boards, instantly destroying components that took years to design and test. The Mars Reconnaissance Orbiter, or MRO, launched in 2005, carries some of the most sophisticated imaging and communication equipment ever deployed in Martian orbit. Its high-resolution camera can resolve features smaller than 1 meter on the surface, while its radio science experiments probe the planet's atmospheric structure with unprecedented precision. But this technological marvel relies on its star trackers, optical sensors that maintain the spacecraft's orientation. By observing the positions of known stars, a debris field from the fragmentation of Atlas could render these star trackers useless by creating false targets or overwhelming their sensitive photodetectors with unexpected light sources. Without a reliable attitude control system, the MRO's high-gain antenna would be unable to maintain its precise aim toward Earth, severing the communication link that allows the spacecraft to transmit its scientific discoveries back to mission control. MAVEN, the Mars Atmosphere and Volatile Evolution Mission, faces different but no less severe challenges. This spacecraft was specifically designed to study how the solar wind interacts with and strips away the upper atmosphere of Mars. Its particle detectors and magnetometers are calibrated to measure the gentle, predictable flow of charged particles from our Sun. But the passage of Atlas could flood MAVEN's sensors with particle flows many times greater than anything they were designed to handle. This is like trying to measure a gentle breeze with an instrument suddenly exposed to a hurricane. MAVEN's delicate sensors could be permanently damaged or saturated, overwhelmed beyond their ability to provide meaningful data. Electromagnetic pulse effects, while not equivalent to the fictionalized EMP weapons of Hollywood thrillers, could still induce currents that damage a spacecraft's wiring. Modern spacecraft carry thousands of meters of electrical cabling, unintentionally creating effective antennas that can pick up electromagnetic energy from external sources. A sudden surge in the local electromagnetic environment could turn these essential connections into conduits for destructive currents. Each spacecraft also carries its own unique vulnerabilities. Based on its mission-specific design choices, Mars Express, the veteran Mars probe from the European Space Agency, has been in operation since 2004 and is showing its age in some of its subsystems. Components already operating near their design limits might not withstand the additional stress from a sudden, turbulent electromagnetic environment. The Trace Gas Orbiter, TGO, is our most recent addition to the Martian fleet. It is equipped with state-of-the-art spectrometers designed to detect trace gases in the Martian atmosphere, including potential biosignatures that could indicate past or present life. But these ultra-sensitive instruments require extremely stable operating conditions to distinguish a true atmospheric signal from instrument noise. The turbulent electromagnetic environment from the passage of Atlas could overload these delicate instruments with false signals, rendering months or even years of observations scientifically worthless. Worse still, the electromagnetic interference could corrupt the spectrometer's calibration systems, requiring complex recalibration procedures that might be impossible to perform remotely. But let's push this scenario to its most catastrophic logical conclusion. What would happen if the passage of Atlas not only threatened individual spacecraft, but also caused a systemic failure across the entire Martian orbital infrastructure? What if the electromagnetic chaos were severe enough to trigger a cascade of safe mode shutdowns, leaving humanity's robotic presence at Mars completely blind? Spacecraft designers integrate safe mode systems as a last resort to preserve the mission's viability when sensors detect anomalous conditions. In safe mode, all non-essential systems are powered down. The solar arrays are oriented towards the sun for maximum power generation, and the spacecraft awaits commands from Earth to assess the damage and attempt recovery. But safe mode assumes that the anomalous conditions are temporary, and that ground controllers will eventually be able to re-establish contact to begin recovery procedures. If Atlas were to create electromagnetic chaos that lasts for weeks, or even months, our Mars orbiters could become trapped in safe mode for an extended period, unable to perform scientific operations or even relay communications from the rovers on the surface. The psychological impact on the Mars exploration programs would be devastating. Imagine the public reaction to the news that all of our Mars orbiters have gone silent simultaneously. Social media would erupt with conspiracy theories about space disasters and government cover-ups. Public support for Mars exploration, so carefully cultivated over decades of successful missions and stunning images, could evaporate overnight. Mission control engineers at JPL and other space agencies would face an unprecedented crisis management challenge. Standard spacecraft recovery procedures all assume that you can communicate with the affected vehicle to diagnose the problem and upload corrective commands. But if electromagnetic interference prevents reliable communication, ground controllers could find themselves essentially powerless to assist their distant robotic charges. This ripple effect would also extend to operations on the surface of Mars. The Perseverance and Curiosity rovers rely on orbiters to maintain regular communication with Earth. Without these relay systems, the rovers would be forced to communicate directly with Earth using their own lower-power radio systems, a process that severely limits data transfer rates and operational flexibility. Even more concerning is the possibility that Atlas could trigger the kind of rare space weather event that astrophysicists have warned about for many decades. If the comet's passage coincides with a major solar energetic particle event or a coronal mass ejection, this combination could overwhelm the spacecraft's shielding systems, which are designed to handle each threat individually, but not both at the same time. The recovery time for such a cascading failure could stretch for years, unlike terrestrial infrastructure, which can be repaired by sending technicians to the affected site. Spacecraft malfunctions in Martian orbit require complex troubleshooting procedures conducted across interplanetary distances, with communication delays measured in minutes. Some spacecraft may never recover from the electromagnetic shock from Atlas's passage. Components damaged by power surges or degraded by prolonged exposure to the bombardment of charged particles might simply not respond to recovery efforts. Missions that have operated successfully for many decades could come to an abrupt end, not due to the gradual aging of their systems, but due to a sudden exposure to cosmic forces beyond their design parameters. The loss of these Martian orbital assets would set back our understanding of the red planet by years, or possibly decades. Scientific investigations that depend on long-term monitoring would be cut short just as they are beginning to reveal crucial information about climatic evolution, atmospheric chemistry, and the geological processes of Mars. But perhaps most troubling is that the failure of our Martian fleet would leave us unable to know what Atlas truly did to the planet. We might find ourselves in the position, knowing that something significant had happened on Mars, but unable to observe or comprehend the consequences until new missions could be designed, built, and launched, a process that typically takes at least a decade. However, even as we ponder these technological nightmares, we must remember that Atlas operates within the realm of solar system dynamics, where even our own sun can be affected by sufficiently dramatic cosmic events. Through its albedo, or reflectivity, the red surface of Mars reflects sunlight in ways that help maintain the planet's current temperature regime. But the passage of Atlas could deposit a significant amount of dark organic dust over a large portion of the planet's surface. This layer of dust is composed of materials formed in a foreign stellar environment, which may have thermal absorption properties completely different from anything currently on Mars. Dark surfaces absorb more heat than light surfaces, a fundamental principle of physics that could trigger a runaway warming effect. In areas where the Atlas dust settles, localized temperature spikes could vaporize subsurface water ice, adding water vapor to an atmosphere already struggling to maintain its chemical balance. The added moisture could interact with the carbon dioxide from Atlas in ways that create conditions for acid rain, further altering the surface chemistry. But this is where the scenario becomes truly concerning. From a terraforming perspective, what if Atlas's chemical contributions don't make Mars more Earth-like, but instead push the planet toward a greenhouse catastrophe similar to that of Venus? Venus, although similar to Earth in size and composition, experienced a runaway greenhouse effect, turning it into an intensely hostile world with a surface hot enough to melt lead and atmospheric pressure that could crush a spacecraft within hours. Mars, with its lower gravity and greater distance from the Sun, would not normally be susceptible to a Venus-style greenhouse effect under normal circumstances. But Atlas introduces variables that have never been tested in planetary climate models. Exotic organic compounds from interstellar space could catalyze chemical reactions that amplify greenhouse warming, far beyond what the addition of carbon dioxide alone could cause. The timeline for such changes could be measured in years, rather than the geological timescales usually associated with natural climate evolution. A planetary atmosphere, when pushed beyond a critical threshold, can undergo rapid transformations, completely altering its character in just a few decades. What begins as a modest enhancement of Mars's existing greenhouse effect could accelerate into an irreversible atmospheric transformation. Future Mars missions are planned based on the assumption that the planet's environment will remain relatively stable and predictable, might find themselves operating in conditions that bear no resemblance to current models. Life support systems designed for the current atmospheric composition of Mars could fail catastrophically when faced with the chemical changes left behind by Atlas. In situ resource utilization, ESRU, the foundational technology that makes long-term habitation on Mars economically feasible, depends on the ability to extract water, oxygen, and even rocket fuel from the Martian environment using known chemical processes. But if Atlas fundamentally alters the planet's chemical composition, these ISRU systems could become useless or even dangerous to operate. Imagine astronauts arriving on Mars in the 2030s and discovering that their atmospheric processing systems cannot function in the altered chemical environment created by Atlas. Instead of producing breathable air, the systems might produce toxic compounds capable of poisoning the entire habitat. Water extraction systems might encounter organic contaminants that render the recovered water unsafe for human consumption, despite sophisticated filtration efforts. The psychological impact on humanity's dream of space colonization would be a catastrophe. Mars represents our nearest viable backup planet, our insurance policy against existential risks that could threaten civilization on Earth. The discovery that an interstellar visitor has rendered Mars uninhabitable, just as we are developing the technology to establish permanent settlements, would be like watching humanity's long-term survival prospects dissolve in real time. But the changes Atlas brings to Mars might not be limited to chemistry, the atmosphere, and the surface. The comet's passage could alter the planet's electromagnetic environment in ways that affect everything, from its auroral displays to the behavior of its dust storms. Mars's weak magnetic field offers only minimal protection against charged particles, making the planet extremely sensitive to changes in the local space weather environment. Intensified electromagnetic activity could affect the ionosphere of Mars in ways that would disrupt radio communications for decades. Future Mars missions could find themselves operating in a communications environment that requires entirely different technologies compared to those we are currently developing. The reliable communication windows that mission planners take for granted could become erratic and unpredictable. The effects of dust storms alone could reshape the strategy for Martian exploration for generations. If the electromagnetic effects of Atlas cause global dust storms to occur more frequently or with greater intensity, the reliable solar power that most Mars missions depend on could become unreliable. Nuclear power sources, currently considered an option for missions to Mars, could become essential for any long-term operations. Perhaps most unsettling is the possibility that we will not fully understand the impact of Atlas on Mars until decades after the 3/10 encounter. Atmospheric chemistry operates on timescales that can make immediate assessment impossible. The chemical reactions initiated by the passage of Atlas could continue for many years, gradually altering the Martian environment in ways that will not become apparent until future missions attempt to operate under the changed conditions. This catastrophic terraforming scenario forces us to confront an uncomfortable truth about planetary engineering. We do not understand planetary atmospheres well enough to predict how they will react to sudden, large-scale chemical changes. Our models work reasonably well with gradual changes that occur over geological timescales, but they have never been tested with the kind of cosmic chemical shock that Atlas could deliver. However, even as we contemplate these environmental nightmares, we must acknowledge that the most dangerous effects of Atlas may not be physical at all. What if the 3/10 encounter unfolds exactly as predicted by the official models, with no dramatic effects, no electromagnetic chaos, no chemical catastrophe? But the public refuses to believe that nothing significant happened. What would happen then if the real disaster was informational, not physical? Part 10, a Don't Look Up scenario. In the modern era, information operates with a chaotic momentum of its own, potentially more unpredictable than orbital mechanics and more dangerous than cosmic radiation. When significant astronomical events occur, the gap between scientific reality and public perception can widen into chasms that completely swallow rational discourse. The encounter of Atlas with Mars on October 3rd created a perfect storm of conditions for an informational disaster. The event occurred during a solar conjunction, when observations from Earth were limited, and scientific data required weeks or months of analysis before meaningful conclusions could be drawn. Most importantly, the encounter involved an interstellar object, an entity whose behavior did not fit established models, a cosmic wildcard, something that fueled speculation far more easily than it provided definitive answers. NASA and the European Space Agency were very cautious in their public communications about Atlas. Official statements acknowledged the object's unusual nature and confirmed plans for observation campaigns during the encounter, but they hesitated to provide the dramatic imagery and speculative scenarios that could capture public attention. This cautious approach, while scientifically sound, created an information vacuum that other narratives quickly filled. Social media algorithms, designed to maximize engagement rather than accuracy, prioritized alarming interpretations of the incomplete data. By the time the official scientific analysis was complete, public opinion could have already been so deeply shaped by misinformation that fact-based corrections would become ineffective. The precedent for disinformation campaigns in the astronomical domain offered little comfort to those hoping for the triumph of rational discourse. The revelations about unidentified aerial phenomena, UAP, by the United States government in 2022, had shown how quickly speculation could outpace official information. When faced with phenomena that challenge conventional understanding, congressional hearings that were meant to provide transparency instead created more questions than answers, fueling conspiracy theories rather than resolving them. Atlas also poses a more complex challenge, as this object is truly anomalous in ways that are difficult to explain simply. The vast cloud of carbon dioxide, the unusual changes in brightness, and the strange orbital characteristics were enough to create a genuine mystery, making even the most outlandish theories seem plausible to the non-expert. The delayed schedule for releasing scientific data further exacerbated the problem. The James Webb Space Telescope's infrared observations of Atlas, taken in August, are still being analyzed by research teams adhering to peer review processes, which prioritize accuracy over speed. Preliminary results might not be released until several months after the October 3rd encounter, creating an extended period when speculation could run rampant, unchecked by factual information. Meanwhile, amateur astronomers and citizen science groups are conducting their own observations with equipment that, while impressive for home use, lacks the sensitivity and calibration of professional observatory instruments. Their images and measurements, shared instantly on social media platforms, could contain artifacts or misinterpretations that professional astronomers would immediately recognize, but which might seem convincing to the public. A don't look up scenario emerges, where this combination of factors creates a situation in which the public believes something catastrophic has happened at Mars, regardless of what actually transpires. If the Atlas encounter produces any unusual phenomena, even relatively minor events, well within the range of natural variability, could be interpreted as evidence of a cosmic disaster. Imagine this nightmare scenario. Atlas passes by Mars on October 3rd without much incident, only producing subtle changes in the planet's electromagnetic environment that require complex analysis to detect. The Mars orbiters continue to operate normally, only engaging temporary precautionary safe mode protocols that reduce science operations. The rovers on the surface experience brief communication disruptions due to scientifically expected fluctuations in the ionosphere. This represents an interesting but non-catastrophic encounter, providing valuable data on the interaction of interstellar objects with planetary magnetic fields. But from the perspective of the mass media, it could be interpreted as evidence of a deliberate cover-up. The temporary reduction in image transmission from Mars created a signal loss, which conspiracy theorists interpreted as proof that something terrible had happened. Technical explanations offered by space agencies with details about ionospheric propagation and spacecraft operational procedures sounded like bureaucratic jargon to an audience already primed to expect dramatic revelations. Social media was flooded with increasingly elaborate theories about what had really happened during the encounter with Atlas. Computer-generated images, purporting to show impact craters on Mars, spread faster than official corrections could be issued. Amateur radio operators claimed to have intercepted distress signals from Martian orbiters, which space agencies refused to acknowledge. The psychological dynamics driving such information flows are well understood by cognitive scientists, but are not yet adequately addressed by official communication strategies when people are primed to expect dramatic events. Normal scientific caution is misinterpreted as evasiveness when official explanations involve technical details, requiring specialized knowledge to understand. They are dismissed as attempts to obscure rather than to clarify. The 2014 presidential election demonstrated how misinformation can quickly reshape the public's perception of reality. The very psychological mechanisms that allow baseless claims of election fraud to persist despite the factual evidence, which is overwhelming, can be easily applied to claims about cosmic cover-ups and suppressed astronomical data, congressional oversight of space agencies, which is intended to ensure transparency and accountability, can actually amplify misinformation if representatives without scientific training demand answers to questions that cannot be definitively answered with available data. Hearings with dramatic testimony about potential threats in space can generate media coverage, treating speculation as established fact when international partners add yet another layer of complexity to information management. The European Space Agency, with its communication protocols and different political constraints, might release information on a schedule that doesn't align with NASA's plans. But this difference in timing could be interpreted as evidence of failed coordination or deliberate information management, rather than routine operational considerations. Amateur astronomers in countries with different traditions of transparency might share conflicting observations or complicate the official narratives. The space agencies of China or Russia, operating under different political pressures, might describe the same event in ways that seem inconsistent with the interpretations of Western scientific agencies. The cumulative effect could be a global information environment, where multiple, conflicting versions of what actually happened on Mars compete for public attention, with scientific accuracy becoming just one variable among many in determining which narrative gains traction. But perhaps most dangerously, the "don't look up" scenario could become a self-fulfilling prophecy. If public pressure forces the early release of preliminary scientific results, which are later proven to be incorrect, space agencies facing congressional investigations and media scrutiny might feel compelled to release interim findings to meet the public's demand for information, but lacking the rigorous analysis necessary for scientific accuracy. These early disclosures, when later corrected by more thorough analysis, could be misinterpreted as evidence of incompetence or deliberate deception, rather than the normal scientific process. This cycle of correction, where dramatic initial claims are gradually tempered by more careful analysis, mirrors the very pattern that fuels conspiracy theories about government cover-ups. The long-term consequences for space science could be severe. The public's trust in space agencies is built over decades, through successful missions and incredible discoveries, could be compromised by failures in information management during the encounter with Atlas. Future missions may have to face a skeptical public, who have been conditioned to doubt official explanations of astronomical phenomena. However, even as we reflect on these misinformation nightmares, we must prepare for the possibility that October 3rd will pass without providing any clear answers to any of the questions Atlas has raised. What happens when the most significant astronomical event of our generation unfolds and leaves us with more mysteries than answers? What happens when the universe refuses to provide the dramatic closure that the human psyche demands? Part 11. If Mars bears the brunt of October 3rd, 2025, the day Mars died. Not literally, of course. Planets do not die as living things do. They do not draw a final breath or fade peacefully into the cosmic night. But on this day, Mars as we knew it humanity's next frontier, our red beacon of hope, ceased to exist as a destination for human exploration. The impact occurred at 1400 hours UTC, when the fragment of Atlas designated AF7 slammed into the northern hemisphere of Mars at a velocity that made a bullet look sluggish. The object, approximately 400 meters in diameter, was composed of ice and compounds, of exotic organic matter previously unseen anywhere in our solar system, delivered a kinetic energy equivalent to thousands of nuclear bombs to a planet utterly unprepared for such cosmic devastation. Within minutes, the cameras of the Mars Reconnaissance Orbiter captured images that would haunt planetary scientists for generations. An expanding fireball, momentarily brighter than the sun in Mars's pale sky, followed by a shock wave that propagated across the planet's surface at supersonic speeds, obliterating everything in its path. The crater, when the dust had finally settled enough for orbital observations to be made, measured 37 kilometers across. A wound on the ancient surface of Mars exposing rock formations that had never seen sunlight since the planet's infancy. But the crater was only the beginning of Mars's transformation into an alien world. The impact had unearthed millions of tons of subsurface permafrost, instantly vaporizing the water ice that had been trapped in the Martian crust for billions of years. This sudden eruption of water vapor in Mars's thin atmosphere created weather patterns that defied every model in the climatology textbooks. Massive storm systems driven by temperature differentials that had never existed in Mars's recorded history began to form just hours after the impact. The electromagnetic pulse generated by the impact overwhelmed every piece of human technology on Mars simultaneously. The Mars Reconnaissance Orbiter, MAVEN, Mars Express, and the Trace Gas Orbiter, humanity's electronic eyes on the red planet, all triggered their emergency safe mode protocols as their star trackers lost their bearings and their communication systems were flooded by radio frequency noise from the ionized debris cloud. But the safe mode protocols assumed that the anomalous conditions were temporary. They were designed to protect the spacecraft during brief periods of instability, not during planetary catastrophes that fundamentally altered the electromagnetic environment for months or years. One by one, as backup power systems were depleted and critical components failed under conditions they were never designed to handle, the orbiters went silent. The loss of contact with Mars lasted for 14 months. For over a year, humanity had no direct contact with the red planet, which had captured our imaginations for centuries. The Perseverance rover, Curiosity, and the international collection of landers that had studied Martian geology and climate all vanished into radio silence. Mission controllers at JPL, accustomed to receiving daily reports from their robotic emissaries, suddenly found themselves staring at blank screens and dead communication channels. The psychological impact on Earth was immediate and profound. Mars had represented humanity's next chapter, our cosmic coming-of-age story. To see it slip from our technological grasp was like watching the destruction of humanity's most cherished dreams. The stock market declined as aerospace companies witnessed their Mars exploration contracts evaporate overnight. Congressional hearings demanded answers that no one could provide. As communication was finally reestablished through emergency protocols and hastily launched replacement satellites, Mars emerged from the radio silence bearing little resemblance to the world we once knew. The planet's entire atmospheric circulation pattern had been disrupted by the impact. What had once been a relatively predictable climate system, with seasonal dust storms and well-understood weather patterns, had become chaotic and unpredictable. Global dust storms, once rare events that occurred every few Martian years, had become the new normal. The planet's surface remained shrouded in a persistent veil of suspended particles, blocking sunlight and rendering solar power unreliable for any surface operations. Temperatures plummeted as the dust-filled atmosphere reflected solar radiation back into space, triggering a nuclear winter effect that lasted for more than 3 Martian years. The radiation environment around Mars was permanently altered by the impact. The impact not only dredged up radioactive material from deep within the Martian crust, but it also created a temporary debris belt around the planet. A chaotic collection of impact ejecta bombarded the upper atmosphere for months, creating prolonged auroras and ionospheric disturbances, which made radio communications sporadic and unreliable. Mars's larger moon had suffered an unforeseen fate, sealing the fate of any future human missions to Mars. Debris from the surface impact had struck the irregularly shaped moon, with enough force to destabilize it from its already precarious orbit. Instead of the 50-million-year death spiral that astronomers had predicted, Phobos began to break apart immediately, creating a debris field that would plague Martian orbit for centuries to come. The fragments of Phobos ranged in size from boulders to enormous, building-sized chunks sent flying in chaotic orbits, turning navigation through Mars's orbital space into a deadly game of cosmic roulette. Any spacecraft attempting to reach Mars would have to weave through a three-dimensional minefield, composed of rock fragments moving at speeds that could turn the slightest impact into a catastrophe. The dream of colonizing Mars, which had once seemed so close to reality in the early 2010s, had vanished within the clouds of radioactive dust that now permanently shrouded the red planet. The meticulously planned Artemis missions to Mars were canceled indefinitely. International treaties on Martian exploration became obsolete overnight, as the planet they were designed to govern had become too dangerous to visit. Private space companies that had invested billions of dollars in Martian transportation systems saw their business models shattered by a single cosmic accident. SpaceX's Starship, designed specifically to transport cargo to Mars, was hastily repurposed for lunar missions and asteroid mining. Blue Origin's Mars landing systems became museum pieces before they could even fly. The scientific community struggled to comprehend the full scale of what had been lost. Mars had once been our natural laboratory for studying planetary evolution, climate change, and the possibility of extraterrestrial life. Rovers and landers had spent decades meticulously analyzing the Martian soil. Now, they were buried under meters of radioactive debris. Their discoveries were lost forever in the cosmic catastrophe. But perhaps the worst part was the realization that the Mars that Atlas had destroyed was irrecoverable on a human timescale. A planet's atmosphere can recover from major upheavals, but this process often takes millions of years. Mars, even if it eventually emerged from the chaos Atlas had created, would be a completely different world from the one that had welcomed humanity's explorers. Over generations, the impact had slightly altered Mars's axial tilt, transforming the planet's seasonal patterns in ways that would take decades to fully comprehend the vast amounts of water vapor and strange organic compounds from its core. Atlas had triggered atmospheric chemical processes that followed no known model on Earth. This was not the slow climate change scientists had envisioned. It was a chaotic, rapid planetary transformation, rendering all previous Mars exploration plans meaningless and obsolete. The repercussions extended far beyond Mars itself. The destruction of humanity's most accessible stepping stone to the outer solar system forced us to completely recalculate our expansion into the cosmos. Instead of using Mars as a staging area for missions to the asteroid belt and the moons of Jupiter, space agencies were forced to develop more complex and costly alternatives to reach these destinations directly. The psychological trauma of witnessing our cosmic neighbor become uninhabitable created a generation of space scientists who viewed interstellar objects with suspicion rather than wonder. The romantic notion of comets as harbingers of cosmic beauty was replaced by the pragmatic understanding that the universe contains forces capable of destroying worlds without warning or malice. Congressional funding for planetary defense programs increased significantly as the reality of cosmic threats became undeniable. The success of the DART mission in deflecting the asteroid The Force, once seen as a fascinating technology demonstration, suddenly became the cornerstone of a multi-billion-dollar planetary protection initiative. designed to prevent future Atlas-like disasters. However, even as humanity mourned the loss of Mars as a destination, we began to understand that the disaster of October 3rd might have revealed something even more alarming about our cosmic neighborhood. If Atlas could destroy Mars through a random encounter, what other interstellar visitors might be quietly approaching our solar system, carrying the potential for even greater catastrophes? Surveillance networks were established to monitor near-Earth asteroids, was quickly expanded to detect interstellar objects, many years before their closest approach to inhabited worlds. The assumption that space was mostly empty and safe was replaced by a sobering realization that the universe is filled with wandering objects capable of altering or destroying planets on timescales much shorter than geological processes. But as we ponder this alternate history, where Mars died on the 3rd of October, we must remember that the universe rarely provides such dramatic closure to its cosmic mysteries. What if Atlas's encounter with Mars proved to be far more subtle and mysterious than our worst fears or wildest fantasies? What do the speculations suggest? What if the 3rd of October passed in silence, leaving us with more questions than answers about our cosmic vulnerability? Part 12. If Mars survived. If Mars survived. The 3rd of October came and went like a cosmic whisper, rather than a scream. The final orbital calculations from the European Space Agency, ESA, placed Atlas's closest approach to Mars at 30.2 million kilometers at precisely 11:17 UTC. No impact occurred. No electromagnetic storms formed. No global dust storm shrouded the red planet in radioactive chaos. Mars continued on its ancient orbit around the Sun, seemingly undisturbed by its encounter with the interstellar visitor Atlas. The first official statement came from the ESA Mission Control Center 6 hours after the closest approach. Comet Atlas 2019I4 has completed its encounter with Mars within all predicted parameters. Martian orbital assets report normal operations. No anomalous activity detected at this time. Further analysis is pending. 42 words that, somehow, sounded both reassuring and deeply unsatisfying within minutes of its release. Social media platforms erupted with a collective expression of anticlimax bordering on outrage. Is that it? Became the top trending phrase on Twitter within an hour. Reddit forums dedicated to Atlas speculation devolved into heated debates about whether that mundane result was a successful scientific prediction or evidence of an organized cover-up. The public's reaction revealed something profound about human psychology and our desires regarding cosmic events. For months, Atlas had captured global attention, precisely because it represented the unknown, the potentially catastrophic, the cosmically significant. Its mysterious behavior and interstellar origin had fueled speculation that ranged from the scientifically plausible to the utterly fantastic. But all of it shared a common assumption that something dramatic would happen as this celestial visitor made its closest approach to Mars. However, the reality of cosmic encounters rarely aligns with human expectations. For narrative satisfaction, the universe operates according to the laws of physics, indifferent to our desires for a climactic ending. Most astronomical events, even truly significant ones, unfold in ways that seem ordinary to observers untrained, to recognize their subtle yet important implications. NASA's subsequent statement, issued 12 hours after the closest approach, offered technical details that satisfied the curiosity of the scientific community, while dashing public expectations of a dramatic revelation. Preliminary analysis of Martian orbital data revealed minor fluctuations in ionospheric density, consistent with predicted interactions between Atlas's ion tail and the Martian magnetosphere, with no structural damage to any orbital assets detected. Surface operations continued as normal. The language was precise, professional, and utterly devoid of the cosmic drama that months of speculation had led the public to expect. Where were the stunning images of Atlas streaking past Mars? Where were the electromagnetic light shows that should have been visible from Earth-based telescopes? Where were the clear signs that an event of historical significance had occurred? The disappointing reality was that most of the dramatic phenomena people were expecting would be largely unobservable to the naked eye. The fluctuations in ionospheric density, while scientifically significant, did not make for visual spectacles that could be easily converted into social media content. The magnetospheric interaction, while significant for understanding the object's behavior near Mars, generated data rather than images. Professional astronomers understood that the most significant consequences from Atlas's Martian encounter might not be apparent for months or even years. Subtle gravitational perturbations, the slightest atmospheric chemical changes, the long-term impacts on Mars's electromagnetic environment. All of this required careful analysis of data to be collected over an extended observation period. But public attention, operating on the dynamics of the news cycle, demanded immediate gratification. The story of Atlas, which had sustained media interest for months through mystery and speculation, suddenly lost its narrative momentum when the October 3rd encounter delivered no obvious drama. The absence of a spectacle created an information vacuum, which conspiracy theories rushed to fill. If nothing dramatic happened, the skeptics argued, why did the space agencies keep their observation plans secret? Why were so few images released from the encounter? Why did the official statements sound as if they were hiding something behind technical jargon? Amateur astronomers, who had spent weeks preparing for the encounter, found themselves in the awkward position of having captured images that showed nothing particularly remarkable. Their telescopes had recorded the journey of Atlas near Mars, but the resulting images looked disappointingly mundane when compared to the calculated predictions that had been available for months. The most advanced ground-based observatories also faced similar challenges in conveying their data for public understanding. Spectroscopic measurements, which revealed subtle changes in Atlas's emission patterns, were scientifically valuable but not visually impressive. Radio telescope arrays detected variations in plasma density around Mars, but these discoveries could not be easily converted into the kind of stunning imagery that could capture the public's imagination. Social media algorithms, designed to promote engagement rather than education, began to amplify increasingly elaborate theories about what the space agencies were hiding, not telling the public the mundane reality of a successful scientific observation campaign was reframed as evidence of institutional secrecy. The careful, methodical approach, characteristic of professional astronomy, was interpreted as a deliberate cover-up. Congressional representatives, many of whom had used Atlas as a platform to discuss space funding and planetary defense, found themselves in an awkward position, having promised their constituents stunning revelations that failed to materialize. House Science Committee hearings had been scheduled to address the Atlas crisis, but were quickly rebranded as routine oversight sessions on NASA's Mars exploration program. The media coverage reflected this shift from crisis to anticlimax. With astonishing speed, cable news channels had prepared extensive programming on the Atlas encounter, but now had hours of empty airtime and very little dramatic content to justify the coverage. Expert panels on cosmic disasters instead found themselves explaining why the absence of drama was actually the most likely outcome. The scientific community faced its own public relations challenges. Researchers who had spent months preparing for the Atlas observations discovered that their preliminary results, while scientifically interesting, did not generate the public excitement that translated into continued funding and support. Successfully predicting a non-catastrophic encounter was less compelling than a failed prediction of disaster. The international collaboration on the Atlas observations, which represented one of the most comprehensive multinational astronomical campaigns in history, received minimal media attention, precisely because it operated so smoothly. The coordination between NASA, JAXA, and other space agencies prevented the kind of conflicting information that might have sustained public interest. Through controversy, the James Webb Space Telescope observed Atlas in the infrared during its Mars approach, producing some of the highest resolution images of an interstellar comet ever captured. But these scientific achievements were overshadowed by public disappointment, as the images did not show clear signs of a cosmic catastrophe. The subtle spectral signatures indicating the unique chemical composition of the core, alas, were far less visually compelling than the dramatic collision scenarios that had dominated pre-flyby speculation. Amateur radio operators, who had prepared to monitor Mars's communication networks for signs of electromagnetic disruption, found themselves recording routine spacecraft operations instead of cosmic chaos. Their sophisticated monitoring setups, poised to capture historically significant evidence, instead chronicled the mundane, yet reliable continuation of Martian exploration. The non-event of October 3rd began to take on a symbolic meaning that transcended its astronomical importance. Social critics pointed to the underwhelming Atlas event as evidence of larger institutional failures in science communication, arguing that researchers and space agencies had failed to manage public expectations for what was always the most likely outcome. A scientifically interesting, but visually unremarkable event. Educational institutions found themselves grappling with student disappointment, mirroring the broader public reaction. Astronomy classes that had followed Atlas for months as a real-time case study in interstellar object behavior saw their students lose interest when the encounter failed to produce overt drama. Teachers struggled to maintain engagement with the subtle yet significant scientific discoveries the encounter had actually yielded. The long-term implications for public support of space science became a source of concern within the astronomical community. If the interstellar visitor, most dramatic in recorded history, could pass through the inner solar system without generating sustained public interest, then how would future missions compete for attention and funding against more immediately compelling terrestrial concerns? However, perhaps most telling was the speed with which public attention moved on from Atlas to other topics. Once the encounter proved less dramatic than anticipated, the comet had dominated the news. Astronomy, for many months, nearly vanished from mainstream media in just a few weeks after its Mars approach. As the scientific data was analyzed, the approach ultimately proved to be far more valuable than any dramatic collision scenario could have been, largely beyond the public's awareness. But this rapid shift in attention may have left us blind to the subtle signs that Atlas's influence on our solar system was far from over. What if its quiet passage near Mars was merely the prelude to a longer, more complex cosmic symphony? What if the real story of Atlas was only just beginning, hidden behind layers of institutional secrecy and public indifference? Part 13. Atlas as a messenger throughout human history. Comets have served as cosmic punctuation marks in the story of civilization. They are omens of change, harbingers of transformation, messengers from realms beyond earthly human comprehension. Ancient astronomers interpreted their appearances as messages from divine forces, warnings encoded in celestial fire, demanding to be deciphered by those wise enough to read the language of the heavens. Atlas arrived in our solar system, carrying evidence that no comet before it had ever possessed. This was not a familiar member of our sun's great family, following a predictable orbit calculated decades in advance. This was a true alien, a visitor from immense interstellar distances, so vast that it carried within it, in its very core, the chemical signatures of stellar environments that may no longer exist, star systems that perished before Earth's continents took their present form. The message Atlas carried was written in a language more ancient than life on Earth, the language of atomic structure and molecular bonds, of isotopic ratios, and crystal structures forged in conditions that have never existed anywhere in our solar system. Every spectral analysis of Atlas's emissions revealed chemical signatures that told stories of alien stellar winds, exotic radiation environments, and gravitational conditions that have shaped matter. According to the laws of physics, operating under extreme conditions that our solar system has never experienced. But what if the message of Atlas went beyond mere chemistry? What if the patterns we have observed, the unusual variations in brightness, the unusual shape of the cometary halo, the vast amount of carbon dioxide suddenly released, represented something more structured than the random behavior of a comet? What if we are witnessing the first attempts at interstellar communication, using a medium that we never thought to monitor for the controlled sublimation of exotic ices? Consider the possibility that an intelligence could manipulate the gas plumes from a comet in ways that create patterns detectable across interstellar distances. A civilization that has mastered large-scale engineering could be capable of embedding information into the orbital and emission characteristics of objects launched between star systems. The message would be revealed over months or years as the object approaches our sun, creating a slow signal that could eventually be detected by any technological civilization monitoring its solar system. The mathematics of this type of communication would be elegant in its simplicity. Binary information could be encoded in the brightness, with variations following patterns distinguishable from natural fluctuations. Complex data could be embedded in spectral signatures that reveal themselves only through careful analysis of emission line ratios. Even the object's trajectory could carry information, with subtle course corrections during its approach creating geometric patterns that would be unmistakable signs of artificial manipulation. The behavior of Atlas, seen from this perspective, takes on a new meaning. Yes, the vast amount of CO2 that once puzzled astronomers might not be just an unusual sublimation, but a controlled release of gas intended to maximize the object's visibility and ensure its detection by technological civilizations. The unusual brightness, the patterns that do not match standard cometary models, could be structured signals awaiting the proper mathematical analysis to reveal the message hidden within. The timing of Atlas's appearance, during a period when humanity has finally developed the technological sophistication to conduct detailed spectroscopic analysis of interstellar objects. It might not be just a coincidence if the object was launched from its home star system thousands of years ago. Its trajectory would be calculated to arrive in our solar system within a narrow window of time, just when our technological development makes us capable of receiving and interpreting complex chemical messages. NASA's James Webb Space Telescope represents humanity's most advanced instrument for analyzing the chemical composition of distant objects. The timing of Atlas's arrival just as this revolutionary observatory became operational has created the conditions for us to extract more information from a single interstellar visitor than was possible a decade ago. If Atlas carries an embedded message, we could be the first generation of humans capable of decoding it. Coordinated observation campaigns by the European Space Agency have generated data sets containing more information about a single interstellar object than anything ever gathered in human history. Hidden within the terabytes of spectral data and orbital measurements, emissions analysis could reveal patterns that only manifest through computational analysis, techniques that did not exist when previous interstellar visitors like Oumuamua passed through our solar system. But decoding a potential interstellar message requires abandoning human-centric assumptions about communication protocols. The signals might be embedded in mathematical relationships that transcend language barriers, like prime number sequences hidden in brightness variations, geometric constants encoded in spectral line ratios, or physical constants represented through isotopic compositions that could be the result of artificial manipulation. The challenge lies in distinguishing between natural patterns and artificial signals in phenomena that are inherently already beyond the limits of our understanding. Interstellar objects inherently exhibit behaviors inconsistent with solar system norms, as they formed under different stellar conditions and followed different evolutionary paths. Separating true anomalies from natural processes that are exotic requires analytical techniques still under development. Amateur astronomers and citizen science groups have contributed observational data that professional observatories might miss due to scheduling constraints and limited telescope time. If Atlas carries an embedded signal, it might be most apparent in long-term monitoring data, collected by dedicated amateur astronomers who can track the object continuously, rather than during brief professional observation windows. The SETI Institute has quietly begun to apply signal analysis techniques developed for radio astronomy to the Atlas datasets, searching for patterns that might indicate artificial interference in the object's behavior. Although no results have been widely published, the mere fact that such an analysis is underway suggests the possibility that Atlas is serving as a medium for interstellar communication, is being taken seriously by experienced scientists searching for extraterrestrial intelligence. The message, if one exists, may not be intended for immediate comprehension. Interstellar communication across millennia would surely involve concepts and information that might require many generations of technological development for humans to fully understand. Atlas could be transmitting a message that only when our mathematical and scientific knowledge has advanced to a level commensurate with the civilization that sent it, will we be able to understand it. The psychological implications of such a discovery would change human civilization in ways that would overshadow any physical impact Atlas might have on Mars or other planets. The confirmation that we are not alone in the universe, and the patient reception of an interstellar message, would compel humanity to redefine its place in the cosmic community and our responsibilities as members of a galactic network of intelligent civilizations. But the absence of a clear message should not be interpreted as proof that no message exists. The most sophisticated communication could be embedded in the behavioral aspects of Atlas, which might only become apparent through analytical techniques yet to be invented. Future generations may look back on our current observations of Atlas and be amazed at what was taking place, how much information we have failed to extract from the dataset. The richest interstellar event in human history, international cooperation in the study of Atlas, has created unprecedented opportunities for global collaboration in decoding a potential message. If the object carries information intended for all of humanity and not for any single nation, then the decentralized nature of current observation campaigns ensures that no single government or organization could suppress or monopolize access to interstellar intelligence. The Atlas encounter may be serving as an unintentional test of our civilization's capacity for rational analysis. Under conditions of uncertainty and speculation, our reaction to this interstellar visitor, the theories we have created, the fears we have expressed, the institutions we have trusted or doubted, may reveal fundamental weaknesses in the decision-making processes of our collective, which could spell disaster when true cosmic threats emerge. The speed with which Atlas became a canvas for every existing anxiety about government secrecy, cosmic threats, and institutional competence suggests that the systems we rely on are more vulnerable to manipulation than we thought. Social media algorithms that amplify sensational content over accurate content have created conditions where speculation can overwhelm evidence faster than scientific analysis can combat misinformation. The Atlas encounter represents more than just an astronomical event. It has become a mirror reflecting our civilization's relationship with the unknown, our trust in expertise, and our ability to distinguish between genuine mysteries and human-made crises. The lessons we learn from Atlas's journey through our solar system may be more important than any physical impact the object had on Mars or other planets. Perhaps the most profound insight to emerge from the Atlas encounter is about impermanence, that our solar system exists in galactic regions, where interstellar travelers are the norm rather than extraordinary events. The rarity of such objects in human historical records does not reflect their actual scarcity, but rather the brief lifespan of our technological civilization, compared to astronomical timescales. If Atlas represents the first of many interstellar visitors that our ever-expanding detection capabilities will identify in the coming decades, then the speculation and our current institutional responses may well set a precedent for how humanity will deal with the entire spectrum of cosmic encounters. The frameworks we develop to analyze Atlas, both scientifically and socially, will shape our response to future interstellar visitors. For generations to come, the datasets generated from observations of Atlas will continue to provide research opportunities long after the object itself has departed our solar system. Spectroscopic measurements, orbital calculations, and emissions analysis represent the most comprehensive study of an object, interstellar, ever undertaken by human civilization. Hidden within this data may be insights that only become apparent as future technological developments provide new analytical capabilities. Graduate students and researchers decades from now may discover patterns in the Atlas data that reveal information for which we currently lack the mathematical or theoretical frameworks to recognize. But the most significant discovery from Atlas's visit to our solar system may not emerge until the 2040s or later, when scientific advancements allow us to extract information from the observations we are making today, without fully understanding their ultimate implications. The international collaboration that Atlas has inspired among space agencies, research institutions, and amateur astronomy communities represents an unprecedented experiment in global coordination around cosmic phenomena. The protocols developed for sharing Atlas data and coordinating observation campaigns could serve as a template for managing future encounters with visitors, interstellar or other cosmic events that transcend national boundaries. But the collaboration also created vulnerabilities. If our current study of Atlas is missing crucial information or misinterprets important models, then the coordinated nature of current efforts could amplify these errors across multiple organizations and nations. The same coordination that makes comprehensive analysis possible could also make systemic mistakes harder to recognize and correct. The contributions of amateur astronomers to the study of Atlas have demonstrated the ongoing importance of distributed observation networks, which can track objects continuously rather than in the short windows of professional telescopes. Future interstellar visitors may be best studied through coordinated campaigns, combining the capabilities of professional telescopes with amateur dedication and geographical distribution. Educational institutions have used Atlas as a real-time case study in interstellar object behavior, creating pedagogical resources that will influence how future generations of scientists approach cosmic mysteries. The teaching materials, observation protocols, and analysis techniques developed during the study of Atlas will shape science education for decades to come. The psychological and cultural impacts of Atlas may prove to be as lasting as its scientific contributions. This interstellar visitor has forced humanity to confront its cosmic isolation in ways that purely theoretical discussions never could. The simple existence of an object from another star system has made interstellar space feel less empty, and extraterrestrial civilizations seem more plausible. Public opinion polls conducted during the Atlas approach have documented a shift in attitudes toward space exploration. Funding, planetary defense programs, and international cooperation in scientific research. These attitudinal changes, sparked by a single cosmic event, could influence policy decisions and resource allocation for decades to come. The encounter with Atlas has also revealed the extent to which modern technological civilization depend on predictable cosmic conditions. Our spacecraft, communication systems, and even our terrestrial infrastructure are all designed under the assumption that space remains essentially static. Between major solar storm events and meteor impacts, interstellar visitors introduce additional variables that our engineering systems and risk assessments are not designed to handle. Mission planning. The protocols that have worked well enough for solar system exploration may prove insufficient for operating in a cosmic environment that includes regular interstellar traffic. The legal and ethical frameworks governing space exploration were created under the assumption that cosmic encounters would involve objects and phenomena originating within our solar system. Atlas has raised questions of sovereignty, environmental protection, and scientific responsibility that current space law does not adequately address. If future interstellar visitors carry messages, technological artifacts, or biological materials. Humanity will need new international agreements to balance scientific investigation with planetary protection, national security concerns with information sharing, and immediate research opportunities with the long-term consequences for human civilization. The Atlas encounter represents a coming of age for humanity, from a civilization on a solar system scale to becoming participants in galactic-scale phenomena. Whether we have passed or failed this cosmic examination, the response to this first great test will set patterns that affect the development of our species. For generations to come, Atlas continues its journey toward the outer solar system and eventually back into interstellar space. It carries with it not only the chemical signature of a distant stellar environment, but also the reflected light and radio waves emitted from a technological civilization taking its first tentative steps toward cosmic maturity. Future interstellar travelers may detect these signs and draw their own conclusions about humanity's readiness to become a member of any cosmic community. Exists among the stars. October 3rd, 2025 may be remembered, not as the day Mars was threatened by an uninvited interstellar visitor, but as the day humanity began to understand that we are not alone in a universe filled with wandering messengers, carrying news from distant worlds. The real question is not what Atlas could have done to Mars, but what it has done to us, and whether we are prepared for the next cosmic visitor following in its ancient trail. The worst-case scenario for Atlas might not have been a planetary catastrophe or electromagnetic chaos. It could be that we learned nothing from this encounter about our fragility in the cosmos, our institutional limitations, and our urgent need to develop better frameworks to understand our place in a more alien, more dynamic universe, and far more dangerous than our fleeting technological civilization had ever realized. Part 14. A final speculation. What if we miss the real story? October 3rd has passed, and Mars continues on its ancient orbit. The spacecraft monitoring the red planet continue their routine observations. As for Atlas, it continues on its calculated trajectory toward the outer solar system. The moment of approach to our neighboring planet, our nearest one, has now become a historical event, no longer a future speculation. However, in the quiet aftermath of an encounter that did not deliver the cosmic drama that months of speculation had promised, a more unsettling possibility begins to emerge. What if our entire framework for understanding Atlas, our focus on impact scenarios, atmospheric disruptions, and potential contamination, represented a fundamental misunderstanding of what we were actually witnessing? What if the real story of Atlas was not about what could have happened to Mars, but about what has happened to our information systems, our decision-making processes, and our collective ability to distinguish between real cosmic threats and manufactured crises? The evidence for this alternative interpretation lies not in telescopic data or spacecraft telemetry, but in the institutional patterns of behavior that have surrounded Atlas since it was discovered. Consider the carefully calculated timing of the information release, the coordination between international space agencies that typically compete for resources and recognition, and the unusual level of congressional interest in what should have been a routine astronomical observation campaign. The space agencies, usually eager to announce their most impressive discoveries, have been more cautious in their announcements. Observations from the James Webb Space Telescope, or JWST, of this object, made in August, were still being analyzed months later. Despite the revolutionary capabilities of the instrument and the supposed significance of studying humanity's first documented extraterrestrial organism with such a sophisticated instrument, NASA's chief scientist, typically enthusiastic about sharing spectacular images and breakthrough discoveries with the tax-paying public, has offered mainly technical briefings and orbital updates, rather than the inspirational content that usually accompanies major astronomical events. The European Space Agency, with its different political constraints and media traditions, has followed surprisingly similar protocols. suggesting a coordination that extends beyond normal institutional boundaries. The absence of spectacular images from the October 3rd encounter may not be a failure of the observation campaigns, but rather the success of information management strategies we were not intended to recognize. If the most significant aspects of Atlas, during its Mars flyby, occurred in spectral bands or at a temporal resolution that does not translate into publicly compelling content, then the lack of dramatic footage might be entirely intentional. Professional astronomers, who typically compete fiercely to publish first and capture media attention, when dealing with significant discoveries, have maintained an unusual degree of collective discretion regarding Atlas research. Preliminary findings, which are typically announced at press conferences and fast-tracked for publication in journals, have instead followed more deliberate review processes, prioritizing institutional coordination over individual recognition. The amateur astronomy community is often eager to share observations that could challenge or supplement professional research, has generated surprisingly little independent analysis of Atlas, despite the object's accessibility to instrumentation. This silence may reflect not a lack of interest, but rather pressure from professional networks to coordinate observations instead of competing for attention. Congressional oversight of space agencies, while publicly focused on routine budgetary and policy questions, may be addressing the classified aspects of the Atlas research, which never appear in public hearing records. Space science committees, which typically scrutinize NASA's most expensive missions, have shown an unusual deference to the agency's expertise regarding its Atlas observation strategy and data release schedule. International space law provides frameworks for managing information about potentially hazardous objects, but these protocols were developed with conventional near-Earth objects in mind. Asteroids, not interstellar visitors whose origins and composition could reveal information far beyond ordinary astronomical significance. If Atlas carries implications for national security or international relations, existing treaties may not offer adequate guidance for information management. The possibility that we are witnessing the first global, coordinated response to an interstellar visitor carrying information too sensitive for conventional public release could explain many of the anomalies in the official coverage of Atlas. Space agencies, intelligence, and political institutions may be grappling with unprecedented challenges for which there is no historical precedent.